Hi everyone. Now I'll be explaining solutions to Codeforce round 663. Okay, let's start from problem A. So quite an easy problem. Well, in this problem we can just print like any arbitrary permutation. So just to print all numbers from 1 to n is enough. Because we have a condition that has to be true, has to be like held for each range. So or on that range has to be at least the length of that range. Well, yeah. So or on that range has to be at least the length of that range. So since it is a permutation, the smallest number you're gonna have here, like in that range, will be r minus l plus 1. And that's it will be fine. This condition will be held because like the smallest number on that range will be r minus l plus 1. Yeah. So it's fine just to print any permutation. Okay, let's go to problem B. So in problem B, you have let me just draw this grid. So since we have only signs like right and down, I think we can just ignore. Let me check. Yeah, so I think we can ignore like all signs that are here. Because anyway, regardless how you will change them, like all cells will lead you to this row. Yeah, to this row and this column. Yeah, so we can just ignore all cells here. So let's suppose here we have a sign, like for example, down. Yeah, then that's a problem. For sure, then we can't reach the last cell. So, which actually means that in this last row, we just need to count number of downs because we need to make them right. And for the last column, we need to count number of rights here because then we can't reach the last cell. So we need to make them down. Yeah. That's problem B. Okay. Okay, problem C. Quite interesting problem. Will be hard for, I guess, many people, but let's try. Okay. Well, in this problem, I think you could try to draw examples of good permutations or of cyclic permutations and notice if there is if there are such three numbers, let's say I, j, and k, such number at the middle is less than numbers as left and right. I mean, not exactly to the left and to the right, but I mean such indexes. Then for sure this permutation is not cyclic. Oh, sorry. Yeah, then it is cyclic. Yeah, then it is cyclic. Mm, yeah. Okay, let me read it. I guess I misunderstood something. I mean, I'm not sure if we need to count number of cyclic or not cyclic permutations. Okay, we need to count number of cyclic permutations, not the other way around. Okay. Yeah. So yeah. So you can try to prove it, but if shortly saying um like if we will be going left by certain edges, yeah, so we'll for sure meet certain number that is greater than the current one. Let's say this was 5, let's say this is like 8, and let's say there is another number, like let's say 7. So, and I claim that there is a edge between 7 and 8, for example. Um, let's suppose if it's not, let's suppose if there is like an edge, let's say to the number that is here, for example. But anyway, that number is still greater than 5. Let it be, I don't know, 9. So then you can just replace that 7 with 9, and yeah, that will be still the same logic. So which means that you will have always that like such 3 numbers if that permutation is cyclic. Okay. I guess I was counting number of not cyclic permutations. That's strange. Okay, anyway, yeah, like never mind. Sorry. Yeah, so which means that you can't have such 3 indexes. So like if you want to calculate, sorry, I guess I'm a bit confused here. Okay, but anyway, let's just try to like figure out how to count either number of cyclic permutations or not cyclic. Anyway, it will be the same because then we can just subtract from total number of permutations. So yeah. So let's count number of permutations that are not cyclic. So actually, we can try to see how they will look like. And actually, the permutation will be first of all increasing, and only then decreasing. Yeah, so it will look like increasing then decreasing. Yeah, the permutation will look like that. And if it looks like that, then it doesn't have any cycles. So for example, if it's first decreasing, then increasing, and something like that, then yeah, so then it is, then that permutation has cycles. Okay, so now we kind of change the problem, reduce it to another easier problem, where we just need to count number of such permutations, where first it's increasing, then decreasing. Might be just decreasing. Okay, that means that zero numbers is increasing first of all on prefix. Well, so now it looks like combinatorics problem. So let's fix number of, like, how many numbers increasing. Yeah, so let's say that I numbers will be increasing, and yeah, so which means that if you have if your array will look like, if your permutation will look like that. So let's say that the length of or number of, like, increasing like a number of this part, the length of this part is I, and the length of that part will be n minus I. Yeah, and for sure that, like, it's clear then that maximum number or number n has to be in this part, because if it will be in that part, otherwise, I mean, if number n will be in the right part, so that wouldn't be, like, first increasing then decreasing. So n has to be at the left. So there is such formula as n choose r, I guess. So we can just calculate number of ways to choose I numbers that will be increasing, and yeah, that's actually it. So we should choose among n minus 1 number, we should choose I number, I minus 1 number, because as we mentioned, number n for sure will be at the left part. Yeah, so that's just for fixed I, but we should do that for every I. Thus, we just kind of for loop through all i's. So let's say that I, yeah, again, I is the number of increasing number, or the length of increasing prefix. Yeah, that's actually it. So yeah. Okay, I hope it was clear. By the way, you should know how to calculate this n choose r by modulo. So if you don't know, just Google it, because now I wouldn't be explaining that because it's gonna take quite long. Yeah, but just Google how you can how you can calculate n choose r. That's actually just n factorial divided by n minus k factorial and k factorial. Like, if you want to choose k objects out of n. Yeah, so since here we need to divide by something, and also you need to take by modulo, so you should also know how to divide by something if you take by modulo. Yeah. So I think for some of you it will be really helpful and educational to learn how to divide by modulo and calculate this n choose r thing. Okay, let's go to problem D. Yeah, I like problem D a lot. That's interesting problem actually. Yeah. So what I did in this problem, I was drawing some examples, and I noticed that if, for example, I have like a square or submatrix, like submatrix, let's say, like, yeah, submatrix or square of even lengths. Yeah, let it be 4 by 4. So each submatrix of that matrix of length 2 has also to be good. Well, if all these four submatrix are good, which means that here we have odd number of ones. Here we have odd number of ones, like in every part. So, which means that in total we will have even number of ones in that square. Which means that it is not possible, like, to make this 4x4 square to be good. Yeah, it's not possible to make it good. Yeah, because as I just mentioned, like, anyway, number of ones will be even, which means that if you can select such square in your like initial grid, differently saying, if n and m is at least 4, yeah, then you can choose such submatrix, such square. Then answer is like no or -1. Cool. That's very important observation, because yeah, that's, I guess, the main observation in order to solve that problem. Well, if it is, then you just print -1. Well, then let's suppose, just for simplicity, that n was less than m. Yeah, and n was less than or equal to 3, and less than or equal to m. So now, after we consider this case, n will be at most 3. So now we might have such grid. Yeah, it might be of height 3 as well, yeah, and 1. But if it's 1, then answer is 0 for sure. Okay, so since the n is at most 3, then here we can do dp. Actually, it's pretty much simple dp. So for each column, we will be trying all possible configurations. Now let's suppose we did here like 1, 0, 1, and now we are trying all possible configurations for that row. And let's say we are like doing something like that. We are making this row go to this configuration, but then we can see that we have a 2x2 submatrix, which is not good. Yeah, so in order to simulate this process, like in order to check if we place it correct configuration in current row or not, we should know last row, like configuration of last row. So let's store a mask, like bit mask, just to know what was the previous row. So let's say we store a previous mask, and then we will be trying all possible configurations for current row. Yeah, like current mask. And we just need to check, like, to ensure that previous mask and current mask, like previous and current configuration, doesn't create any submatrix of size 2 with even number of ones. And yeah, so in order to simulate this process, you also need to maintain current row, right? Because it's like you just want to know like on which row you are. So thus we need these 3 parameters. Actually, we don't need like mask as a parameter. We will be just trying just like for looping through all possible configurations. Yeah, so thus we can just store such mask. So sorry, such dpi ref mask, which will store the minimum cost to make the read or first I columns be correct or good. Yeah. So, and the time complexity of that solution will be, so you're iterating through all rows. That will be m. Then you have 2 to the n's different previous masks, and for each such state, you will be iterating through all current configurations. That's also 2 to the n's. So that will be 2 to the 2n. And yeah, I think that's actually it. So this is the time complexity. So which is fine. Okay. Yeah. As I hope it was clear. If you're not sure, for example, like what is the cost of transitions, like so for example, if you have a current mask, like if you want to, for example, to put certain configuration here, like in this, let's say in this column, how many changes you need to make. So for example, if you want to make it, let's say like 101 for example, but previously it was, let's say, 001. So yeah, so you just need to calculate how many I guess digits you change it. Yeah, pretty much simple. And so for example, you also need to check if previous mask and current mask doesn't create any submatrix of size 2 by 2 with even number of ones. That's also easy to check. Yeah, so I hope it was clear. And let's go to problem E, also a cool problem. Well, I actually had pretty much the same, I guess, idea as with editorials solution, like editorial solutions. Okay. So we have a graph. So let's just do DFS and select DFS 3. Yeah, let me use another color. Let's say we have a 3, but not just 3, it is a DFS 3. And yeah, let's say like that, and we will also have like back edge. By the way, it is not possible to have such like back edge because it means that we just have 2 such edges, and in problem statement says that it is not possible to have multi edges. Yeah, it doesn't contain multiple edges. Yeah, so it is not possible to have such edges. Yeah, let's say something like that, and the cool thing about such DFS3 that all back edges goes only like only goes up. It doesn't go to another like sub let's say sub tree, or yeah, it goes only to ancestors. Yeah. Okay, so let's do some observations here. So let's suppose if the depths, so let's denote depths as number of levels. So for example, here we have like 1, 2, 3, 4, like 4 levels. Yeah, levels or depths, you can like say anything. So let's say if a depth of that tree is at least n divided by 2 rounded up. Yeah, if depth of that tree is, let's say depth of that tree is at least n divided by 2 rounded up, which means that we have a node with um, with a depth at least n divided by 2. So then it means that we can just choose that path. So for example, so then we will like solve that part, like solve that condition. Well, let's suppose like another case when it's not possible, like when the like opposite case, when the depth was less than n divided by 2 rounded up. Yeah, so now let's try to figure out how we can solve that case. So let me just copy that tree. Well, in that case, we can just, for each depth, we can try to match all nodes in that on that level. Like for each level, we would trying to match all nodes in that level. So yeah, on each level, we like if we will just, for example, match like, let me use another color. Let's say if we will be matching like that. Yeah, so on each level we will we'll have, after matching, at least one left node, which we couldn't match to anything, like to any other node. For example, here on that level we left with one node, and on that level we left with one node. So in the worst case, number of such left nodes will be is just depth of that tree, because on each level we can have it more, like exactly, in the worst case, exactly one such node. Yeah. So which means that we would have at most sorry, let me check. Yeah, so which means that we will have at most that many unmatched nodes, and we'll have at least at least that many number of matched nodes. Well, since depth of the tree is less than n divided by 2, so this number will be at least n divided by 2 rounded up. Yeah, so depth of tree can be at most n divided by 2 rounded down. Okay, so it might be not clear why, if you take induced graph of a pair of some like nodes, of some pairs, so that So it's not clear if that will have at most 2 edges or not. Well, let me prove that quickly. Well, for example, let's take 2 pairs on the same level. Yeah, so for example, let's take this pair and this pair. Well, for sure they wouldn't have any edge, like any induced edge, because that pair doesn't have any edge between. That pair doesn't have any edge between. So yeah, so which means that if 2 pairs are on the same level, they don't have any common edges at all. Okay, so then let's consider pairs that are on different levels. Well, if it is like that, if it is if these 2 pairs kind of not one above another, then also they don't have any common edges at all. But it is possible that you could have such case when one pair is above another one, just above another one. Well, only then, in this case, you'll have 2 induced edges, which is fine. So this is, I guess, just my proof, short proof, brief. And yeah, actually that's it. So I think everything was fine in terms of explanation. So yeah, so thank you so much for watching, for joining my video solutions. I hope you learned something new. So I want to wish you good luck in your competitive programming improving. And yeah, so see you next boom. So see ya in the next video. Bye bye.